Welcome everyone to our presentation on the optimization of bus routes. I'm Ishtiyaq and together with my teammates and we'll guide you through our project. Moving on to the next slide. Rooted in the 1950s, work of George Danzig and John Ramser, route optimization has evolved into advanced traffic management systems. Today's systems not only manage traffic flow by adjusting signal timings on busy roads, but also enhance road safety with features like fatigue detection for drivers. This multifaceted approach aims to streamline urban commutes, elevate road safety, and reduce travel times and fuel consumption, marking a significant leap in urban traffic management. And here we are with the public transportation challenges. The urbanization is accelerating, and with it, the challenges for public transportation are also growing. By 2050, 68% of the world's population will be living in cities. This is leading to an increase in congestion, causing an increase in travel time and wait time for commuters. So, by the importance of public transportation optimization, by optimizing public transportation, we aim to create a system that's not only more user-friendly but also environmentally friendly. Our goal is to reduce greenhouse gas emissions and tackle inefficiencies such as traffic jams, increased travel times, and prolonged wait times. And here we are with our proposed project. So our approach involves creating an agent-based model to simulate commuter behavior, bus routes, and congestion patterns. We then apply search algorithms to find the most efficient routes and schedules, considering distance and population density. Using AVMS, we can simulate how both people and buses move within a city. This representation allows us to experiment with various scenarios and optimize bus routes with accuracy. So in our model, the agents are the passengers and the environment is the city itself, complete with bus stops, traffic lights, and roads. Passengers wait at bus stops and board or depart buses which follow optimized routes based on our algorithms. We'll look into three of these related works on bus route optimization, the optimization of bus stop locations using GIS technologies or techniques, optimizing bus lines using the genetic algorithm, and implementation of the Ant-Colony algorithm for bus network optimization. So this study used GIS technique to model the location of bus stops in Amman, a city in Jordan, to find optimal travel time and serviceability of stops. Optimization significantly reduced travel time, particularly on streets with redundant bus stops. The limitations of the study stems from the trade-off between travel time and walking distance. As mentioned before, in areas with insufficient bus stops, the models added additional stops, resulting in increased travel time. The second related work here considers stop density, arrangement, and passenger population to propose an improved design for public transportation. The K-means clustering algorithm is then used to cluster relevant data to find areas of interest where there will be high population density. The genetic algorithm finds ways to link said areas of interest. Longer distances traveled were penalized while passenger intake was prioritized by the fitness function of said algorithm here. And in this study, the road network and existing bus lines were converted into a graph data structure initially. Then the Ant-Colony algorithm was implemented to create new bus routes where existing routes and transfer regulations at nearby bus stops were considered. Alterations in the total passenger flow across the network were used to find the best approach for network optimization. Overall, the optimization efforts have resulted in a reduction in the proportion of the entire line network, indicating an improvement in overall structure of the bus network. So as you can see, the simulation of the optimal path according to this algorithm is output to the screen based on a specific source destination data where the population to path cost ratio of each node at each level is calculated and the minimum value at each level is added to the optimal path throughout its traversal. The population data is negated initially as the minimum population to path cost ratio is taken into account since the algorithm is built on the generic A-star search algorithm, where the minimum value should be tracked at every level of the graph and the higher population is taken in consideration at the same time, because the purpose of the algorithm is to serve more people with lower path cost at the same time. Here, as you can see, the implementation of the A-star search algorithm being implemented on this sample graph by taking in consideration of the minimum population to path cost ratio as it traverses from the source level to the next set of adjacent nodes or the next level until it reaches the goal level, where we actually end up getting the optimal path that services more people per route. Moving on to this slide, this is the illustration of the entire project being implemented here, as we initially implement the extract.py file, which is being executed to extract the coordinates out of some database or some CSV file and writes the coordinates data with the names to a JSON file. And then moving on to the next execution of adj.py file that creates a graph data structure of adjacent list of the coordinates, and we have the rendered graph data structure so that it can be displayed on the screen by the pass.py file being executed. And finally, we have the generated heuristics and population density data that is being generated by the oxy.py file for the A-star algorithm, which is being executed by the main.py file to generate the optimal path that is maximizing the passenger services. And finally, we have the output of our project or our A-star search algorithm being implemented, taking in consideration of the population to path cost ratio. And to conclude, we were successfully able to implement the A-star search algorithm, and for individuals who are willing to work on the GIS technology or some other AI related technology, they can use this algorithm. And for further reference or future reference, we are planning to implement the algorithm in a manner that it will actually show the optimal path on a more realistic map. So thank you for your patience, for staying with us, and we really enjoyed doing this project. Thank you all.